Alicia Sahara, and I'm a high schooler, and I'm going to be the chair for Isn't Shabir Ali. Isn't Shabir Ali is a 10th grade student at Newton South High School in Massachusetts with a strong focus on astrophysics and astronomy. He has taken advanced coursework in quantum mechanics, leads multiple school clubs, is in an active
Thank you very much for that introduction. Um, so yes, as was said, I am a 10th grader at Newton South High School. Um, so dark matter is inferred from systematic discrepancies between observed gravity and the mass energy of luminous matter. These discrepancies appear consistently across spiral and elliptical galaxies, galaxy clusters, and the large-scale cosmic web. Flat rotation curves in galaxies indicate that the mass is proportional to the radius, far exceeding the mass of stars and gas. Cluster dynamics and lensing confirm mass far beyond visible matter, and the consistency, scale independence, and persistence of these observations indicate a dominant, non-luminous component shaping spacetime and cosmic structure, thereby affecting the gravity around it. Independent methods that measure this all converge on the same conclusion, that the universe contains more mass energy than is visible to us. Now, galaxy rotation curves show velocities inconsistent with luminous mass. Cluster dynamics using the virial theorem and hot gas observations reveal large mass deficits. Gravitational lensing maps total mass directly, and it often shows peaks unassociated with visible matter. And other cosmological measurements of structure growth and CMB anisotropies also require dark matter. And the convergence of these observations across independent methods excludes systematic error or observational bias as explanations. In general relativity, gravity corresponds to the full stress energy tensor, including energy density, pressure, motion, and stresses. Gravity probes total mass energy, and not just visible mass. And so observed gravitational discrepancies imply a significant fraction of mass energy is invisible. Dark matter is thus not an arbitrary addition, but a necessary contributor to space-time curvature. Its influence is measurable across galaxies, clusters, and the cosmic web, consistent with relativistic predictions. And so, not only is dark matter just an addition to special relativity and general relativity, it is rather an integral part of them. Gravity reflects the macroscopic organization of energy within spacetime. Stable energy distributions create persistent curvature, influencing motion and large-scale structure. Dark matter operates as a gravitationally active but non-luminous component, detectable through its effects on orbital dynamics, cluster potentials, lensing, and structure formation. Its presence demonstrates that gravitational phenomena encode both visible and invisible energy distributions. Now, observed orbital velocities in spiral galaxies remain constant far beyond the luminous disk. Keplerian predictions, which say the velocity at the certain radius is proportional to 1 over square root of the radius, fail. And they say that also that the mass in the certain ring around the center must increase with radius. Now, the implied mass distribution is extended roughly spherical and dominates at large radii. Now, this pattern is also universal across galaxy types, sizes, and environments, demonstrating that halos of unseen matter, aka dark matter, are a fundamental galactic feature, and our universe would not be sustained without those. Clusters exhibit gravitational potentials far beyond what luminous matter can produce. Virial analysis of galaxy velocities and hydrostatic equilibrium of intracluster gas indicate masses 5 to 10 times greater than luminous mass. Gravitational lensing directly maps mass through spacetime curvature, confirming mass concentrations unassociated with visible matter. Lensing also reveals offsets between baryonic and dark matter, demonstrating independent mass distributions. Dark matter drives cosmic structure formation. Its early clumping during cosmic inflation seeded gravitational potentials into which baryonic matter fell, forming galaxies, cluster, and filaments. Therefore, without the dark matter that was in the early universe, our our structures in our current universe would not have formed. Simulations without dark matter fail to reproduce observed large-scale structure. And so the inclusion of dark matter matches observed clustering, filamentary networks, and halo mass functions. Dark matter determines both the timing and the topology of cosmic evolution. Gravitational influence depends on mass energy quantity, distribution, and embedding in spacetime. Dark matter makes these dependencies explicit. Identical baryonic systems can evolve differently in distinct halo environments, aka with different dark matter concentrations. And so this demonstrates that gravity is sensitive to both local and global energy organization, and that dark matter's distribution dictates galactic morphology, cluster dynamics, and filamentary connectivity. Evidence from rotation curves, cluster dynamics, lensing, and cosmology form a coherent, self-consistent picture. Dark matter is a natural outcome of energy organization in spacetime, not an arbitrary addition. Its study refines our understanding of gravity, reveals how large-scale structures form, and may uncover new principles governing energy, mass, and spacetime. It is central to both astrophysics and fundamental physics, linking observations across scales. Thank you. Does anyone have any questions?
By the way, that's nice presentation. Thank you, Shabir Ali. Yeah,
All
so
right,
if
thank you.
no one has any questions, so we can